Previously on development length in concrete, I introduced to you this ACI equation for development length, and it included all these factors. I did miss one here. Lambda, it's the lightweight concrete factor. Okay. Oh, and so lightweight concrete is weaker, and so you need a longer development length. And really, this lightweight concrete factor goes with the square root f prime c. They always go together. Lambda square root f prime c. That's a description of the tensile strength of the concrete. Okay, let's talk about each of these variables in turn. The location factor. Okay, so as I explained earlier, when you pour the concrete like this, okay, so the concrete gets placed this way, the top has worse concrete than the bottom. So that means that at the bottom, you have a shorter development length, and the top, you have a longer development length. And this factor is 1.3 if you have 12 inches of concrete below your bar, and 1 if you do not have 12 inches of concrete below your bar. Another thing that happens, I forgot to mention last time, bubbles come to the top, and they can accumulate underneath your bars. So I should have made that white, bubbles. There we go. In this case, 1.3 equals this factor, and the factor is 1. And then all these factors, if it's good, it's 1. If it's bad, it's greater than 1. Here's something to think about. What if you made a T-beam, but you want to, when you make the T-beam, you pour it upside down. So here's the formwork. Here's your bars. And then you pour in the concrete. Okay, so you pour the concrete in like this. And then when you use the beam, you use the beam like this. Okay, so you got the bars up here and these bars down here. In this case, I know those bars are on the top, but when you poured the concrete, they were on the bottom. So these right here, the location factor is 1. The location factor is 1.3. So it's, you know, that T stands for top bar effect is what we call it. But it's the position of the bar when you poured the concrete, because this all happens when the concrete is still green, when it's wet. Okay, so keep that in mind. Okay, the coating factor. If you have epoxy coated bars or green bars, and they're close together, and I'll share with you exactly what close together means later. 1.5. If you have epoxy coated bars and they're far apart, 1.2. And if you have regular bar, it's 1.0. Okay. The bar size factor. Remember, the bond stress was proportional to D over 4. What we did earlier, we had this. We had dFs over dx equals 4 mu over d. Okay. That d was in the denominator, but we're figuring out the grip strength. Solve for that, you get this. Just remember, uh, it's harder oh, this is exactly opposite what I said, sorry. The bad one is 1 and the good one is less than 1. Okay, so remember, it's harder to grip a bigger diameter rope, right? And so it's worse. So for number 7 and larger, you just use the equation with a 1, but for number 6 and smaller, the development length is 20% less, 0.8. Okay, the lightweight concrete factor, okay. 0.75 for lightweight concrete, and or you could do this equation here. And those of you who, again, you took 3210, remember this is from, we think that FCT is 6.7 square root F prime C. And so you remember in our class when we did this, it wasn't 6.7. We got something like 7.1 or 7.4. And so we did this exact experiment in our class, and we ended up with something like 7.1 square root F prime C. And so what they're saying is you can use a lambda bigger than that 0.75. Okay. Okay. There we go. But you can't go above 1. Okay. Confinement factor, C plus KTR over dB. That whole thing has to be less than 2.5. C is the minimum of the cover or the spacing over 2. So this is the cover, which is usually 2 inches, right? Because it's or 1.5 inches, or this spacing divided by 2. Okay, whatever's less of that. And you can think of it as tributary width, like that to that. Okay, so the left or right side, whichever's less, not bigger. This here is a measure of the stirrups. Okay, this is what we've been calling AV, the area of the stirrups. S is the spacing of the stirrups. N is how many bars you're trying to hold together. And if this is just too hard for you, you can just say KTR is 0. Okay? That's a lot. You take all these things and you put them into here. That is pretty rough. And so ACI, to make your life easier, has taken those things and put them into a table that takes into account the confinement factor. This one is probably the hardest, and the size factor. We, in this class, are going to use this table. Okay, so here's the table. Okay, what you need to know, you only have 4 choices. Are you good confinement and spacing or bad confinement and spacing? And are you small bars or large bars? And remember, the dividing was number 6 and smaller, and number 7 or larger. But what is this good confinement or bad confinement? And you can take this as 1 or 1.5. Okay. And I believe that 1.5, oh, it's not the upper limit. Okay, so are you good confinement and spacing or bad confinement and spacing? And it made me think of Wizard of Oz, if you've never seen that. When Dorothy first gets to Oz, I think her name is Glenda, she comes and goes to Dorothy, are you a good witch or are you a bad witch? And so are you good confinement and spacing or are you bad confinement and spacing? So if you're good confinement and spacing, it's 1.5. And if you're bad, 1.0. Okay. Okay. So good. The definition of good is the clear space in the bars is at least D, 1 bar diameter. The cover is at least 1 bar diameter, and you have minimum stirrups over the whole development length. Yet another reason to always have stirrups. You will always have a space of a bar diameter, and you will always have a cover of a bar diameter. So this really is it, right? You have at least minimum stirrups. So if you have stirrups, you are here, okay? Good number 2. You don't have stirrups, which again, bad idea, but you don't have stirrups, but you space the bars 2 bar diameters apart, and the cover is at least a bar diameter. I have made a table that gives you the minimum width of the bars if you want to do this. So it's the minimum width of the beam. So if you want to space your bars at 2 bar diameters, I tell you how many bars you can put in a certain width. I have a table for that, and it's because of this. And this is if you don't have stirrups. Okay, and bad means not good. Okay, so here's this table again. Okay, this means stirrups or space greater than 2D, 2 bar diameters. Okay, and you're going to be using one of these 2, small or big. Okay, you still have to know the top bar and epoxy bar factor and the lightweight concrete factor. But what you get here are the only difference are these fractions. And to show you which one is the best and which one is the worst, well, obviously this is the worst, this is the best. But what about these 2? Okay, so here we go. I've taken that table and I've just done it in terms of those fractions. This is the best, this is the worst, and this is the bronze medal. Okay, gold, silver, and this is bronze number 2. So in wrestling, they have gold, silver, and 2 third places. But this is actually 4th. Okay, no, what am I talking? What? I've done this completely backwards. Wait, let me try this again. That's worst, not silver. Well, for some people, 2nd place is the worst you could do. They'd rather lose than be 2nd, but I'm not like that. Okay, gold, silver, bronze, and worst. That's really sad. 4th is awesome, but not in this case. 4th. Okay, got it? To summarize, you're going to use this. And so we had all those lectures just to tell you where this stuff came from. Let me clean this up. And then what you're going to do, if you have stirrups, you're going to use this box right here, okay, because you have stirrups. And the only choice is you have number 6 bars or number 7 bars, 6 and smaller or 7 and larger, and you'll use these 2 equations. But remember that this is LD over bar diameter. So after you get this number, don't forget you still have to multiply it by the bar diameter. Okay, that I think, oh, there are other factors. Let's just finish this real quick. If you have more, remember how you pick the steel, like AS required is 4.3 inches squared, but you pick 5 number 9s and it was 5 inches squared. And so you only needed 4.3, but you picked 5, whatever your development length is, you really only needed 4.3. You didn't need 5. So you get to reduce it by what you actually needed divided by what you picked. And that can be a pretty significant reduction, okay? Other items, you can't have greater than 10,000 PSI concrete into this equation. The square root of F prime C has to be less than 100. Oh, I'm glad we talked about this. This is super important. I don't care, I don't care what the equation says, the development length is at least 12 inches, okay? You can't have less than that. Oh, another topic, bundled bars. Sometimes you can't get a bar big enough to give your AS. This is like for gigantic, huge beams. And so you have to bundle the bars together like that. So what's the development length when you bundle 3 or 4 bars together? You take the single development length bar and you increase by 20% if you group them 3 together, and you increase it by 1/3 if you group them 4 together. But remember, the equation is LD over DB. What do you use for that? Okay, because you're going to get some number, and so LD is going to be that number from the table, but you need to multiply it by a bar diameter. Do you use the bar diameter of 1 bar? Or what you do is you get an equivalent diameter by taking the total area of the 3 or 4 bars, set it equal to a fake single bar, and then find, so this is the area of 1 bar. So this is the area of 1 equivalent bar, and figure out what that diameter is, and that goes in there. Okay, we are done with straight bars. The next lecture will be, what about these things? Like what is the, remember this? How long does that have to be so it doesn't slip out of the column? But that's for next time.